And welcome to NASA's Jet Propulsion Laboratory. We are so excited to have you here for the NASA Social talking about Earth Now. Thank you for coming. Give yourself a round of applause. For those of you watching at home, we have 100 people here at Jet Propulsion Laboratory today and for tomorrow, and they have come from 22 states and 2 additional countries outside the United States, and they are going to spend the next 2 days speaking directly with our scientists and our engineers, getting a behind-the-scenes look at what we do here at JPL. Also, they can learn a little bit more about our missions, how they work, and feel more involved, because this is your space program. So far to date, NASA has held 72 of these events since 2009. They're held around the country at 10 different NASA centers and several affiliated facilities. We've had almost 5,000 participants at these 72 events. I think we'll kick it over the 5,000 mark a little later this month when the MAVEN mission launches from Florida, and they're doing a NASA Social there as well. These events, like I said, sometimes you're coming in to learn about missions that are planned for launch, and I will say we're going to talk about 3 missions that will be launching in 2014. These are all Earth science missions. And in 2014, we will be holding NASA Socials at those launches. So for those of you here and those of you watching, if you've never been to one of these events, watch for these coming up. Follow NASA Social on Twitter, and you will get a heads up when we're going to be doing registration for those, because I think everyone should come to at least one. So for the next 2 hours, we'll be talking about these Earth missions. A lot of you may not have even known that NASA does a lot of Earth missions, but they're, in fact, about 1/3 of what we do here at JPL is done to study Earth. You probably don't even realize that a lot of that data is getting to you through weather and climate forecasters. In some cases, the National Hurricane Center can use data from NASA missions. It's going to policymakers. It's going to businesses. This is all data that, again, we're putting it out there, but we want you to know exactly what is there, how we're studying Earth, and how it makes a difference for all of us here. For the next 2 hours, we're actually going to be showing you views of our home planet, and we'll start with the first one. And I hope I will see that on the monitor. Views of our home planet taken by missions across the solar system, starting with this one. This view seen by the crew on Apollo 8. It was a picture that wasn't even in the plan to be taken, but the astronauts grabbed their cameras, black and white in color, and they snapped that image. That was Christmas Eve, 1968. A lot of people feel that was the most important environmental image ever taken because we had never seen our planet like that before. We had never seen it just out there in space and see how fragile it is. And it's probably no coincidence that, just a little over a year later, the first Earth Day was established. People started taking a more increased interest in what we're doing. And not long after that, NASA started sending up fleets of satellites to study different elements of Earth. CSAT went up in 1978 to study our oceans. And since then, we have sent up a fleet of satellites bringing back Earth data. And to explain to you what we do today to study Earth, we'll show you this.
Quietly, like a night bird, floating, soaring, wingless, we glide from shore to shore, curving and falling, but not quite touching. Earth, a distant memory seen in an instant of repose, crescent-shaped, ethereal, beautiful.
Like Apollo 15 astronaut Al Warden, who uttered these words, "Sometimes you have to step back to see just how delicate our planet is, and to experience the wonder of it." Hello, I'm Dr. Amber Jenkins, and I work with the scientists who study our home planet here at NASA's Jet Propulsion Laboratory. I'm here in JPL's Space Flight Operations Facility, the nerve center for an amazing array of deep space missions. But there's more to JPL than just studying other planets. We also keep an eye on our home planet, Earth, with nearly a dozen instruments that watch over the land, sea, ice, and the atmosphere. Let's take a look at the satellites and instruments JPL builds for NASA. They take many different paths to get their data, a bit like bees buzzing around a hive. Some of JPL satellites are small enough to fit inside the trunk of a car. Some are much bigger. And each one tells us something unique about the pieces of the puzzle of planet Earth. About 70% of the Earth's surface is covered by water. The oceans are home to some of the most amazing plants and animals in the world. Millions of people depend on the oceans for food and for fun. The oceans store energy in the form of heat. When the JASON-2 mission uses radar to bounce microwaves off the ocean's surface and measure the height of the seas all over the globe, we can see what's really going on. Our oceans have been getting warmer in recent decades, causing them to expand and global sea level to rise. In this map, we've exaggerated the peaks and troughs so you can see how water temperatures affect sea surface height. The blues are areas of cool water, and the reds show regions of warmer water where sea level has risen. The amount of heat stored by the oceans can have a huge impact on our climate. Knowing the facts and the places where warm and cool water are at any particular time gives scientists a fantastic tool for tracking climate change all over the world. At JPL, we also care about what's going on the land and how ice and glaciers on the land's surface change. Everything is constantly changing, even gravity. NASA's twin GRACE satellites show how gravity changes from one month to the next. This time, red is where the planet's gravity field has grown slightly stronger. Blue shows where the gravity field has become slightly weaker. We can really exaggerate the differences to see them better. By watching how gravity changes, we can track how water and ice move around the planet. See that blue hole covering Greenland? It tells us that the ice in this area is shrinking. Okay, we've looked at the land and at the sea. What about the atmosphere? With its hurricanes and ever-changing nature. AIRS is an infrared instrument that flies on board NASA's Aqua satellite. It helps create global maps of air and surface temperature, of carbon dioxide, and of water vapor. These are important greenhouse gases that can change our climate. Check out this 3D view of carbon dioxide at 18,000 feet above sea level. Warmer colors like yellow and red show hotspots where there is more carbon dioxide. Where is all this red coming from? It comes from both natural processes and human activities. You add carbon dioxide into the air every time you drive a car or use electricity made from burning fossil fuels like coal. JPL has many ways to take the pulse of our planet from space. Our scientists and engineers work with space agencies and institutes around the world to track Earth's vital signs. New missions will be going up soon to beam back even more clues about the oceans, land, ice, atmosphere, and how our climate is changing. I hope you've enjoyed our little tour. Remember, our planet, a small blue dot in the vastness of space, is all that we have. So let's take good care of it. Earth. It's your future and our mission.
Gives you just a little bit of a taste of what we do. And the first guest that I am going to introduce to talk to you is the gentleman who is, in fact, the Deputy Director of our Earth Science Directorate. So he knows every one of these missions and everything coming up. He is Jim Graf. He has been at JPL since 1974, working on various missions. I first met Jim in 1999 when you were working on QuickScat, which was an effort to get satellite in space to study winds that had to be done within about a year's time, and they managed to do that. Following QuickScat, Jim left Earth and went to Mars for a little while. He actually was the project manager for the spacecraft there at the back of the room, the Mars Reconnaissance Orbiter, and following that, after spying on Mars for a little while, that mission is still going, by the way. Many, many incredible images of the surface of Mars come from that. But Jim decided to come back to Earth and take up this position leading really the directorate with all of these different missions as Deputy Director. So Jim Graf, Welcome. Thank you so much for coming.
Well, welcome to JPL. And they've given me 10 minutes, so I've got a lot of material to get through. Then we're going to have a question and answer right after that. So if you've got some questions, just let me know. Let's start with the first image, please. That's our planet Earth. But that planet is very difficult to understand. It's very complex. And when you start looking at a planet, you have to start realizing you're measuring a lot of different variables or items to understand what's happening. And you have to measure them over 3D. You got to worry about what's happening in the atmosphere, at different layers in the atmosphere. You have to worry about the surface, and essentially what about the land surface, what about the water surface. And then you have to worry about what goes on underneath the surface of the land. And I'm going to tell you a little bit about what we measure as we go and we look at this in a 3D version. The other thing to keep in mind is you're looking at this temporally. You're looking at it over time. It's not just what's happening right now, this instant. It's what happens over this week, over this month, the year, and the decade. All of that plays into understanding what's going on with Earth. And then just when you think you got it all worked out and you're making the right measurements and you think you've got timescales down, Mother Earth comes along and throws a little monkey wrench into you. Throws up a volcano, throws an El Nino, and pretty soon you say, okay, all bets are off. So this is a very, very complex system that we have to understand. Your planet is really giving us fits, and we're doing everything we can to try to understand what's happening here. So let's start talking about some of the three-dimensional measurements that we do make. This is a picture of a graph that's called the Keeling curve. I don't know how many of you are familiar with it, but the Keeling curve actually measures the amount of CO2, carbon dioxide, directly above Mauna Loa. Keeling went out there in 1958 and he started saying, I'm going to start measuring this. And he just put a device up, started measuring the CO2, and watched it over a period of time. The little sawtooth that you see there, the little ones, is the Earth breathing. That's what happens on a natural cycle over the course of a year in the northern hemisphere. CO2 goes down, the CO2 comes back up. But if you look at the general curve, it's going up. If you looked at this curve and were able to take the measurement back in pre-industrial age, you'd see that all the way down to about 280 parts per million. These are parts per million that you're measuring there. And it was a big flap in the papers that on May 2nd, it got to 400 parts per million. So what does that tell you? It says the carbon dioxide in the atmosphere is going up. So that's a greenhouse gas that's contributing to heating of the atmosphere. So this is one of the measurements that we have to make. And one of the subsequent speakers will be talking about a spacecraft being launched next July, July 1st, called OCO. It's the Orbiting Carbon Observatory. And its measurements will be made just like this, but looking down from space and over the entire sunlit portion of the globe. So it's not just in one place. So we'll start understanding what's happening, where the CO2 is coming from, and where the CO2 is going to. The sinks and the sources of CO2. So that's one of the important things that we have. There are other elements about the atmosphere that you have to worry about. If you sit down here, do you like smog? The answer is no. That smog's bad. Well, a big constituent of smog is ozone. So we don't want ozone down here in the troposphere, down here where we breathe our air. However, if you go up into the stratosphere, well above where the planes fly, all of a sudden you do want your ozone there because you talk about the ozone hole. If the ozone's not up there, then we get the high energy radiation particles that come down, and that's not good for us. So when we start making measurements about our planet, what we're really trying to do is understand these different chemistries all over the globe. And in some cases, they're beneficial. Some cases, they're not. We've got to measure them high. We have to measure them low. We have to measure them over a period of time to see what's happened. In the next view graph, I'm going to move from the atmosphere. I'm going to move to the water. And this is an interesting chart. This has been compiled by our sister agency, CNES, the space agency from France, as well as NASA here, and represents 3 missions that we've flown to date. Starting in about I think it was 92, we got launched. Topex, Poseidon, and Jason 1 and Jason 2. We do that because the spacecraft wear out when they're up there, so we have to get new spacecraft up there to continue the measurement. So over this 20-year period, what you're measuring is the height of the oceans, the average height of sea surface. And what does it tell you? It tells you that the level, the mean level of the oceans have rising about 3 millimeters per year on the average. That's a little bit more than 1/10 of an inch. Over the 20-year period, we've seen about 2+ inches of rise in the average height of the oceans. This is very important if you're starting to say, hey, what's going to happen in 30 years? And what's going to happen to the ports and the beaches as the sea level continues to rise, as we get storm surge on top of high tides? So all of that plays into what's happening in this planet. As you heard in the movie, there's actually 3 components to this rise that we're thinking of. The first one is the fact that as the planet gets warmer, the oceans get warmer. As water gets warmer, it actually expands. So that contributes to some of it. Another portion of it is that you have a lot of loss in Greenland and in Antarctica. They're steadily losing ice and snow. That is coming off of the land and going into the water as it melts. So that's increasing the sea level. Then the last one, of course, is you have glaciers all around the world and mountains that are melting and falling back from the ocean. As they go up into the mountains and melt, that water comes down, and that contributes. So that's that whole rise there. But remember what I said. You got to measure it over a period of time, and Mother Nature does throw a little bit of a monkey wrench into you. If you look in the upper portion up there, you'll see a dip on that curve. And you say, okay, the ocean's been rising, you're measuring it, and all of a sudden it dips. Where's the water go? So some of our scientists were able to find that out. It turns out, if you remember back in 2010, 2011, there were tremendous floods down in Australia. Also, flooding was happening in South America. The water actually evaporated out of the oceans, moved and landed on the land itself. And so we saw that dip. But what happened when all that water flowed off? It went back into the ocean, and we went back up to the curve that we're looking at here. So it's very important to be able to measure this over a long time series. We have a mission going up also in the next, we were talking about 5 missions that will be launched in a period of about 12 months starting next spring. And one of them is Jason 3, which will continue this time series and give us a continued assessment of what's happening. The other players in that now are not just CNES, the French agency, and NASA, but also EUMETSAT over in Europe, and NOAA here, who produces your weather forecasts, are also supporting this activity because this is a very important measurement. Next view graph. Okay, so we've talked about the atmosphere, we've talked about the water. Let's go ahead and talk about the land, the surface itself. What you're seeing here is a small image, and it might look strange to you, but let me see if I can explain to you what you're looking at. It's a land image from Taiwan, and we flew overhead with a radar that looked at the surface and measured the contours of the surface. Shortly thereafter, there was an earthquake, and we came back overhead again and measured the change. So those little undulations and those concentric circles represent actually modulations, an increase in height. Each one of those cycles is about an inch. So it's gone up an inch over a course of 5 or 10 kilometers because of the earthquake. It's moved the Earth. It's squashed it. It's moved it up. It's made changes to it. We're starting to be able now, with our instrumentation, to be able to measure those changes. Let's talk about going under the surface. Next view graph, please. This is Etna. You guys know about Etna? It just erupted last week. You saw pictures of lava coming up, and you saw planes were diverted away from it. It's on the island of Sicily. What you're looking at is a time lapse of the magma chamber inside the mountain actually coming and pushing the mountain up and down. The range is +6 to -4 inches. So you got a 10-inch range that's happening over this 10-year period. So as we fly overhead with our spacecraft, we're able to make measurements here and actually measure the height of the magma chamber and what's happening. And so when you get to the red, you've gone up about 6 inches. So this is the whole, this is what happens when you talk about the subsurface. The whole world is moving on the surface and under the surface, and we have to understand what those elements are. If we go to the next view graph, we'll bring it back home. What happens in our own LA basin here? What you're looking at is aquifers that are underneath the basin that are actually charging, recharging of water, and then the water gets pumped out. So you're actually looking at the earth here as it takes in water and lets it go. The average height is going up about 2 inches and down about 2 inches as you go over the course of the 7 or so years that we've been making these measurements. I must admit, I must say that a lot of these measurements that you've seen come from ERS-1 spacecraft, Earth Resources Satellite, which comes from Europe. So you've got magma, you've got water moving under the surface, you've got the surface moving, you've got the atmosphere. It's a completely dynamic system that we're trying to understand here. Each one of these measurements is great in its own and helps us, but we want to put it together. So the next view graph, we got to start thinking about cycles. Again, what I said is, if you look at sea level rise, that has impacts on the ports and what's happening there. Sea level, what happens? Water evaporates, goes into the atmosphere. What happens then? Well, that affects our weather. One of the biggest parameters we have that goes into your weather forecast is understanding what the water vapor is. So on a scale, this is really influences us on a daily basis, and we want to make that measurement. Then it rains, and we want to understand where it's raining. And then you get the fresh water that stores. And you want to measure what the heights of the lakes are and the rivers are. You want to know how much fresh water we have out there. And then again, it goes into the groundwater. You're measuring aquifers. As the aquifers increasing or decreasing, which way are they generally going? A lot of aquifers around the world are actually going down in the amount of water that they have in them as we pump more and more water out of it. There's not enough recharge associated with it. Then you have soil moisture, because that's critical to growing. So you talk about cycles. You've got to understand not just the individual elements, but you want to understand the whole cycle. And this is only one cycle. There's the energy cycle, there's the carbon cycle, there's a whole bunch of them, all of them working with one another or against one another at different times. So understanding the planet here is really a challenging task. Next view graph. So we talked about understanding the planet. Well, we have to understand the planet not just on our vantage point, but from a global perspective. What happens here affects us now, and we certainly want to know what's happening. But what's happening here may be caused by what's happening on the other side of the planet. For instance, El Nino. You have activity in the Pacific Ocean. That affects our rainfall here, our rainfall in the Midwest. When we say there's an El Nino, you can have more rain or less rain depending upon what's happening. So you can't just say, hey, I'm going to look at my little area of the planet. You have to look at the entire planet. Scale is important. It's very important to understand what's happening all around. When a volcano goes up, what happens? It spews into the atmosphere a lot of particles, and that affects the sunlight that actually comes through and gets down to the planet, to the surface here. So a volcano on the other side of the planet can actually affect us here. Scale is very, very important. Next view graph. So what do? From space, we make lots of measurements. We try to make uniform and calibrated ones. If you went out, if you took 1,000 people and you said, okay, you all have your own device, go out here, here, and here, and here, and make your measurement, I'll bet you those devices would not be well calibrated. And when you get all of your data back, you'd be measuring, well, am I measuring a change on the phenomena I was trying to measure? Or is it because Joe Blow over here didn't have the right calibration? In space, we calibrate one instrument. We spend a lot of time making it happen. And then we apply that over the entire globe. So we get a good calibrated sense of what we're looking at. We can have frequent coverage. We try to have a real global view of things. And we create that long time series that I've been telling you about. It's not just enough to look at it today. We've got to look at it over a decade or longer. So what are we doing about that? Next view graph. NASA has got a fleet up here, and I haven't counted them, but there's like 15, 17 different spacecraft that are flying up there right now. All of them are looking at different phenomena, some on the surface of the planet, some looking at the atmosphere, some looking at the sun to understand what the sun's input is to us. Some trying to look under the surface at the changes that are manifesting itself. So it's a very complex system of which JPL has contributed a tremendous number of instruments and spacecraft to this endeavor. What are we going to do in the future? Let's look at the next view graph. We have 5 launches coming up from JPL, and there are 2 more from our sister centers that will be happening in the period starting next spring till spring of 15. First one, I got to tell you, they're all different. They're all making different measurements, and they're all different sizes. No one size fits all. So the first one is called RACE. You can barely see it over here on the left-hand side. That's a picture of parts of it right there in the pictures on the left. RACE is what we call a CubeSat. Anybody here know what a CubeSat is? Excellent, excellent. Would you like to see a full-scale model of what that spacecraft looks like? Right there. That's it. This is 3D printing that came and created a model. What this will do, it'll be launched, and it'll go into space, and it'll make water vapor measurements. A lot of young engineers at JPL are learning how to build spacecraft and how to build instruments and putting this together with the University of Texas. And we're going to fly it next summer. So that's the first one. That's the little one over here. These are roughly to scale, by the way. The next one is RapidScat. So sometimes we build new ones. Sometimes we save money and we try to take parts of old ones and put them together, and that's what RapidScat is doing. And I believe Howard Eisen is going to be talking later. He's in the back of the room about that. So I don't want to steal his thunder on it, but that is a vital measurement to help us understand the wind velocity at the surface of the ocean. And when you say, well, what does that mean? Well, wind at the surface of the ocean drives the ocean currents. The ocean currents have heat, and they distribute that around the planet. So if you want to understand ocean circulation and the energy cycle, you want to understand that. But it also, the weather forecasters use it for better weather forecasting for you, as well as also for tracking hurricanes and things. So he's got a real challenge trying to put one of these up very cheaply. The second one is Jason 3. Jason 3, as I mentioned earlier, will continue that vital measurement that we've been talking about of the height of the oceans, and continue that for probably another 3 to 5 years after its launch. Then we have OCO2, which is will measure the CO2 column, the carbon dioxide column. Remember, like the Keating curve, only the inverse. You might say this is 2. You might say, well, what happened to 1? We tried to launch 1 a couple of years ago, and it didn't make it off the launch vehicle. There was a failure in the launch, and it wound up in the ocean. So we have a second one to go up to replace that measurement. And the last one in this time period is SMAP. SMAP is soil moisture active passive. And if you look at the model in the corner back there, that's a 3rd scale model of this. That antenna revolves around. It's going to be, now that's 2 meters. That's a 3rd scale. So the full scale one will be 6 meters. That's about 20 feet across. And it's going to rotate once about every 4 seconds. And that enables us to look at the entire globe in 3 days because of what we're trying to do. And we're measuring the amount of moisture in the soil with that mission. So those are 5 missions starting next spring that we will be putting up to try to help you to better understand your planet here. So that's what I have. Take some questions.
Thank you so much, Jim. Because as you can see, we have a ton of great spacecraft and so much science. Questions for Jim can be submitted via social media using the hashtags NASA Social and Earth Now, and our social media team, of which I am a member, will take those, we'll get answers from Jim, and we'll get back to you online. So thanks very much, Jim. And here's your CubeSat. All right, I am Stephanie L. Smith. I am a member of the social media team here at the Jet Propulsion Laboratory in the newsroom, and it is my distinct honor to introduce you to some of the people behind the missions. So, as Jim mentioned, if you'll direct your attention to the back of the room, to that 1/3 scale model of SMAP, which stands for Soil Moisture Active Passive, we have two team members here to tell us a little bit more about their very unique spacecraft, how it works, and the science they're getting ready to do. So we have Narendra Das, who is a research scientist, and he is joined by his colleague, Erika Podest, also a research scientist on the SMAP mission. Take it away, Narendra.
Hi, it's my pleasure and privilege to talk to you guys. I'm a scientist working for the SMAP mission. And as you could see, it is already being introduced. This is the satellite which is being introduced, which is a 1/3 scale model of SMAP. And as mentioned, this is a very unique satellite because of its antenna size and the type of work it is going to do. So let me start this satellite a little bit. Erika, could you please push that red button? So as it was mentioned that this antenna is going to rotate like at least 14 RPM. Rotation per minute, and while it rotates, it will measure the soil moisture using two different technology like a radiometer and a radar. So it has a passive part as well as an active part. So the passive part is basically just observing the Earth's radiation in a microwave frequency, and the active part actually will send an emission towards the Earth's surface, a target, and receive what emission is backscattered and getting back, and it reflects to this receiver, and that is how it will measure some of the variables on the Earth's surface. And that variable basically will be helped. It's known as brightness, temperature, and backscatter that will help us to retrieve soil moisture. So that is how it's going to work. We have a small animation here, which I would like Stephanie to put it on the screen. Yeah, so as you could see on the screen, it says soil moisture active passive. So you see this is the same spacecraft which is already launched in future, and which will be about 680 kilometers above the Earth's surface. As you could see, its antenna rotating in space and time. As the spacecraft go forward, it keep on measuring, and you see as the antenna rotates, it scans the Earth's surface in a circular fashion. So it covers quite a bit of real estate when it go forward in space and time. So this swath it measures, it's around 1,000 kilometers. So every footprint of this passive measurement is nearly 40 kilometers, and the radar footprint, which we'll be processing here in JPL, will be at 3 kilometers. So you could see the width of the swath basically, and it right now passing over the Great Lakes. So this way it will make nearly 14.5 revolution around the Earth's surface. So in the whole one day. So if you put together all this 14.5 revolution, you can see something like this over the Earth's surface. But if you put together all the 3 days of these swaths, it will cover the whole surface. So 3 days is quite a bit of an optimal way to measure soil moisture, to see its dynamic change over space and time.
Thank you so much, Narendra.
Yeah.
Go ahead and join us on stage here. And Erika, your research focuses mostly on using satellites for studying wetland ecosystems and the freeze-thaw cycle. Is that correct?
Correct, yes.
Can you tell us a little bit more about that?
Sure. So our satellite, SMAP, will not only measure soil moisture, but it's going to measure the land surface freeze or thaw state. So what does that mean? What we're looking at is whether the surface of the land surface, is frozen or thawed. And this is really important to know because in the northern high latitudes, the seasons drive whether the vegetation absorbs carbon dioxide from the atmosphere or if it releases carbon dioxide into the atmosphere. So when the vegetation is frozen in the wintertime, think of it as just frozen sticks, and there's a minimal exchange of gases between vegetation and the atmosphere. But in the spring, when the land surface thaws and the vegetation thaws, there's an enormous surge of water in the land surface. You've got snow melting, you've got water on the ground, the trees are thawed out, and they can draw water, and they start what's called the growing season. And this is extremely important because that's when vegetation starts to take in CO2 from the atmosphere. Now, if you remember Jim Graf's graph on Keeling's curve, you saw that cycle. That's the Earth breathing. And that's because primarily of vegetation in the northern high latitudes that's breathing in the summertime. During the growing season, it's taking in an enormous amount of carbon dioxide from the atmosphere. So that's what we're looking at as well with SMAP, whether the land surface is frozen or thawed, which will help us assess the growing season length and the variability in the growing season from year to year.
Okay, I think we're going to have time for 2 questions in the house here. We have a microphone runner, Jari. So if you have a question for Erika or Narendra about SMAP, just go ahead and raise your hand, and she will bring it to you so that people watching at home can hear your lovely voice. We do need to let Erika get out into the field today. She's going to be doing some field research in our local mountains for another Earth sensing mission. So keeping one eye on the clock for you, because science never sleeps. Any questions about SMAP? There we go.
Hi. It's actually about the design of the satellite. It looks pretty unique from the others that we've seen. Can you tell us a little bit about how that design came to be?
Actually, it has a legacy of hydros. So soil moisture being measured, right now it's being measured by some of the existing satellite, has a very coarse spatial resolution, like around 40 to 50 kilometer, which is okay for some of the applications like climate and weather. But most of the time, soil moisture is required in applications like agriculture, applications like watershed management, applications like health, drought, and landslide, flooding, and all kind of. So that requires a very high spatial resolution of soil moisture going from 1 to 10 kilometer. So based on the application. So based on the existing technology of radiometer, if you need to measure at that particular high spatial resolution, you need a huge antenna, which is not feasible in space. So it has to be done through such a way that it incorporate radar and radiometer both. But the problem with radar is that if you measure soil moisture, it's very noisy. It's not very accurate. So this kind of framework came into existence, like which we are doing and building this satellite. What it does, it merges radiometer as well as radar observation. So the radiometer observation actually is very accurate to some extent, and it's very optimal. But it doesn't have the spatial resolution. Radar observation, on the other hand, is very noisy, but has the advantage of very high spatial resolution, like 1 to 3 kilometers. So what we are going to do, we blend the better part of both of them to make a spatial resolution of 9 kilometers. So which would be very much good for a lot of applications, like for agriculture, weather, drought monitoring, flood forecasting, those kind of applications. That's why this spacecraft has both radar and radiometer mounted, and it will use the same antenna. So it works like the radiometer is on, then the radar is on, the radiometer is on, then the radar is on. So that's how this whole technology came into being.
And to add to Narendra's answer, the technology that we're using here, microwave remote sensing, allows us to observe the surface of the Earth regardless of any kind of weather condition or day or night conditions. And that's really unique because with optical sensors, we have problems whenever there are clouds. So here, we don't have to worry about that.
Except for some very, very heavy rainfall, rest of the time, this radar can, this instrument can monitor 24/7.
Great. Any other quick questions in the house? Yes, they're in the back of the room. Can we get a mic runner to you? Keep your hand up. Don't be shy. We'll put the social back in NASA social.
How is this mission going to be ground-truthed?
Okay, so that's a very big, extensive program going on called CalVal program, called Calibration and Validation of the SMAP measurement. So I'll talk about the soil moisture calibration validation. Erika will talk about the freeze-thaw validation. So in soil moisture validation, what we do, there are various ways to do it. One is measuring the soil moisture in situ. That means there are instruments there which measure soil moisture in a watershed, or by using some other satellite, or by using some model. So our focus is mostly using soil moisture measured on surface. So we have designated that into the core sites as well as candidate sites or sparse network. So our most focus is on the core sites, where we do on a grid scale size or in a watershed, we do lots of measurement in a spatially dispersed way. And that provides us kind of a average soil moisture in a grid scale or a pixel scale at which we will be measuring and retrieving soil moisture. So that kind of campaign goes on for a month or so, where people also go and measure soil moisture, and also we have instrumentation. So the advantage of instrumentation is that it can go for a longer time period. So we keep measuring that watershed or the grid scale for a long period of time, and we have some kind of upscaling or scaling function. We scale that soil moisture, bring it to satellite scale, and then validate the soil moisture.
All right, thanks so much, Erika and Narendra. Don't forget to tweet your questions if you think of more later.
Okay, thank you.
So you know that NASA's keeping an eye on the Earth with an entire constellation of spacecraft. I would like to introduce my colleague, Doug Ellison, who is a visualization producer here at the Jet Propulsion Laboratory. He is going to demonstrate for you a free tool that you can use at home to see where all of NASA's Earth-sensing satellites are at any given time, and another tool that shows you data sets. So this data is yours. Take it away, Doug.
Thank you, Stephanie. Good morning, everybody. So that movie you saw earlier on, the introduction movie to a lot of Earth sciences here at JPL, that movie actually was done kind of in a very short schedule, very small budget. And we cheated. We didn't use traditional animation software for most of that movie. We actually used our real-time computer game engine tool to make that footage. And that tool is now one we've wrapped up. We've put it on the web for anyone to use anywhere around the globe completely for free, and it's called Eyes on the Earth. Let's roll the video. We've got a little demo for you. So this is what Eyes on the Earth looks like. Any Mac or PC can use this tool by going to eyes.nasa.gov/Earth. And you can see the current location of a whole fleet of NASA's climate-observing spacecraft. You can see something called the A-Train down there, a bunch of spacecraft that all chase each other in orbit. And you can bring in the data these missions are collecting, in some cases hourly updated. This is a snapshot of air temperature at 10,000 feet. This is carbon monoxide. You can see plumes of carbon monoxide from slash-and-burn agriculture there. Ocean topography, you've heard about Jason 2 and soon Jason 3. They're doing measurements like this to track ocean height. This is the ozone hole. This is a measurement of ozone over Antarctica. And you can see there's some in the north, but there's less in the south. You get a seasonal variation. One of my favorite data sets, the GRACE gravity data set. We measure the Earth's gravity field every month with the GRACE spacecraft. This isn't the lumpiness of the gravity field. This is the lumpiness of the change in the gravity field. And you can see things like the Amazon rainforest filling up with rainwater and getting heavier. You see it lightening out as that water runs back out into the ocean. And you can contrast that to somewhere like Greenland, where you only see a trend in one direction, the weight of ice that is lost from Greenland. And we can also go and ride on board these spacecraft. You're going to hear about the RapidScat mission later on. There's going to be riding on board the International Space Station. In fact, the bottom left-hand corner there, right in front of that little white module, just left of center, that's where RapidScat is going to be. And you can also look at future missions, missions that are on the drawing board, being built, being planned. Here's the SMAP mission. You've seen the model at the back of the room. Here's our version of it in Eyes on the Earth, spinning at the right rate. You can have a look at the spacecraft, see its solar panels, the instruments, what sort of orbit it's going to be in. And other future missions we get in here as well. This one's Jason 3, the latest in a kind of a long line of multiple missions dedicated to measuring the topography of our oceans, not just for ocean rise, but also warm and cold ocean currents as well. And as the last spacecraft I think I'm going to look at is OCO2. There we go. Here's OCO2. You can see lots more besides as well, some of which aren't even off the drawing board yet. They're more kind of nice-to-haves rather than projects in progress. And here's the OCO2 mission. And its orbit takes it over the poles, and you can watch how that orbit changes. But most importantly, you can see the spacecraft, but the important thing is the data these missions are collecting. We're putting it in your hands, so you can have some visibility into what the scientists are looking at. And of course, the obvious question, if you're looking at a data set like this, like carbon monoxide is, well, that's great on Mac or PC, but I want an app for that. And of course, there is one. Earth Now on the iOS store or the Android store, you can see the exact same data in your hand with Earth Now, or on your desktop or your laptop with Eyes on the Earth. That is our tools to share with you the spacecraft and the data these missions are collecting. Thank you very much indeed. Stephanie, I'll hand it back to you.
Thanks so much, Doug. All right, now on to RapidScat, which Doug mentioned. We'll be hitching a ride on the outside of the International Space Station. To tell you a little bit more about this very interesting project, we're going to bring up a couple of people from the mission. Gentlemen, if you'll join me on stage with your props. We have with us both the project manager and the project scientist. So in the blue is Howard Eisen. He is the project manager. And in the green is Ernesto Rodriguez, who is the project scientist. They'll be telling you more about RapidScat. It's interesting inception story, all the parts that came together to make this spacecraft and the accelerated time scale that it's on, and then how it will use microwaves. Yes, a low energy version of the same microwaves you use to heat up a burrito will be used for science. And they'll tell you more about how it will measure wind speed and direction on the ocean. Gentlemen?
Good morning, everyone. Sometimes we develop brand new instruments and brand new spacecraft as the need arises. Sometimes we find creative ways to use what we already have. There was a mission that went up in 1999 called QuickScat, which did a fantastic job of using scatterometry to understand the interactions between ocean winds and waves. And Ernesto will share with you some of the results from that mission and show you how they apply here to RapidScat. But the International Space Station, which was essentially completed as an assembly about 3 years ago, wasn't originally designed for a lot of external science. And the space station community wanted to promote that, and so they offered up opportunities about 2 years ago for people to propose instruments to be put on the outside of the station. An engineer here named Rob Gaston, who had worked on QuickScat, realized there was a lot of leftover hardware from QuickScat which could be utilized for this purpose. And so what you're seeing here is kind of a recycled mission. We've taken flight spare hardware, we've taken engineering models which are used in the development of that other mission, and in this case we're applying it to a new purpose on a new spacecraft, that being the space station. And the space station gives us lots of advantages because it already acts as our host. It provides power, it provides attitude control, it provides a communication path for us. All things that we would need to build if we built our own free-flying spacecraft like we had to do with SMAP. So we can roll the video. We'll show you a little bit about how this mission will occur. Of course, all of our missions start with a launch. This is a SpaceX Dragon. Falcon 9 is the name of the rocket, and the spacecraft on top here is called the Dragon. And this was an earlier launch out of Florida. They successfully launched out of Vandenberg a few weeks ago, so now they're capable of launching out of both coasts. But like all station missions, we'll go up out of Florida. There you see the Dragon in free flight on its way to the station. There have been 2 successful missions to date that have actually brought cargo to the station. There's our future home, the space station. And this is going to highlight the Columbus module, which is actually a European module that's on the station. Some of the modules are provided by Japan, by the US, by different partners. And here's showing the sequence. We're inside the Dragon. This is the Dragon, and it has this area called the trunk. And the payload gets pulled out. And the payload actually launches as 2 separate pieces. You can see one piece being pulled out there. And they're separately brought over to the space station and attached to the end of the Columbus module. So what you see on there now at the end of the arm is the instrument portion, which has the rotating antenna and most of the electronics related to the instrument. What's already installed there is the nadir adapter, which gives us the view looking down at the Earth and provides the direct communication back to the space station. We've had to actually convert protocols. We have an instrument that was designed to work on a satellite built by Ball Aerospace, and we launched a similar spacecraft with the Japanese back in the mid-90s. We've had to convert that into the kinds of protocols that the space station uses. And that's what a lot of our new hardware development is converting communication protocols, power sequences, things like that. And with that, Ernesto?
Okay, so you may be wondering why anybody would care about winds. Of course, you've heard about hurricanes, and those are very, very important. So one of the reasons that we'll show you in a video in a little bit is our instrument is able to measure the winds every day across the globe. And so certainly if you're sitting in Louisiana or the East Coast, it's a very important thing. But there's another reason, much more important in my mind, of course, not to the people that are getting hit by the hurricane, but in my mind anyway, we're caring about the winds. And I don't have a cool illustration, but I have a cool analogy. Think of the Earth as not the Earth. The Earth is, the Earth part is almost an afterthought. It's really the ocean. We really live in the water planet. And the ocean is like a huge flywheel. It stores all the kinetic energy, all the motion energy. It also stores a lot of our heat. You know, even in winter, the ocean doesn't freeze all the way through. And the reason that happens is because it has all that heat. And it also stores a lot of the gases that we put out. All the CO2, if the ocean were not there, right now we'd be close to Venus. So what's powering this flywheel? Think of the winds as a bunch of unruly mice going around and making the flywheel run around. And so really understanding these unruly mice is what we're trying to do in a global sense. And they're interesting mice because just like regular mice, they're affected by the sun. So when the sun comes up, they have energy. They start to get energy through the day, and they start to blow. They blow in different ways during the time of day. As they blow in different parts of the ocean, they start to extract water vapor. That forms clouds. The clouds reflect the energy back into space, and that keeps us cool. It also rains, so it takes water from one place to the other. But think about the problem of trying to monitor these unruly mice globally. The problem that we have right now is that because they're affected by the sun, you know, they have breakfast, then they get going, then they get tired, then they go to sleep. And right now we have a bunch of satellites that are only able to take snapshots during breakfast, during lunch, or at night. And there's no way that we have to put them together. So the space station is really cool in the sense that it has an orbit that throughout the period of a year will allow it to visit all places in the Earth at different times. So we'll be able to look at the mice at all times during their daily cycle, and also to be able to tie all these other satellites that are going on at the same time, and being able to bring them together. Because right now, they're telling us different things, and we don't know how to put it together. So it's a recycled mission, but the science that it can do is really, really cool. So there's a video, I think, that we can see right now. One of the things that you may be wondering is, how in heaven's name can your microwave measure the wind? Well, it doesn't. It's the real truth. What it does is, when the wind blows over water, it ruffles the water. And so those little ruffles in the water actually reflect energy back to the radar. And the more it blows, the bigger the ruffles are, the bigger the energy that we get back. So by spinning this antenna, we can actually get the different levels of energy that are coming back. And by spinning it, we can also watch it from different directions. So we not only get the wind speed, but also get the wind direction. So that allows us to get this global view of what's going on. So this is, you know, the satellite from which I'm project scientist, which was a precursor to this one, for which I'm also project scientist. It's low tech, in times of low tech, but it's actually able to get this global picture of what the ocean, what the winds are doing during the entire day. And this is in 1999, a whole hurricane season. And what you'll see, as you start to see names pop up, are different hurricanes developing and moving towards the United States. Some of them hitting the United States, some of them missing it altogether. And in reality, the way we have of dealing with them is to send airplanes. And we can only send airplanes close to the United States. We don't know whether they're coming or not unless we see them all the way in Africa where they form. And so by having this instrument at the same time as a bunch of other instruments, we'll be able to get daily and maybe better than daily pictures of these hurricanes as they move across. And so really the power of having this global picture, not only hurricanes, but typhoons, the Indian monsoon, all sorts of weather phenomena. We are able to get daily snapshots of things that up until, and this is hard to believe, up until 15 years ago, the best that we had were ships with little anemometers going around and missing most of the world.
Thanks so much, gentlemen. So now at this point, we can open up the floor to questions. Who has questions about our RapidScat mission? Oh, don't all go at once. Well, I, for one, would like to know, what is the biggest difference between QuickScat and RapidScat? Is there a huge improvement? Is it merely a follow-on? What is the relationship between those two missions?
from a hardware standpoint, the core instrument is basically the same because we're literally using the spares and the engineering models that were left over. We pulled this stuff out of 15 years of storage, brought it down to our spacecraft assembly facility, and started powering it up. And amazingly, it all powered up. And it actually behaved in performance testing the same as the old hardware did. So there's a few differences because of the orbit that we're in. We're flying on the space station, which flies lower. So we're at 400 kilometers altitude instead of 800. So we see a narrower swath, just because we're looking to the side all the time. And as we move down, that means we actually cover less area because we're looking less to the right or left. But because we're lower, we get a stronger reflection. We actually go with a smaller antenna, which is beneficial because the room inside this Dragon capsule is pretty small. And so we made a couple of changes to deal with that. But from a performance standpoint, we should see very similar performance. The orbit, however, is different, and that has an effect on the kinds of things that we see, and in particular the fact that we don't revisit the same place at every time of day. And Ernesto could elaborate on that.
Yeah, so again, as I mentioned earlier, the fact that we don't revisit the same time of day at the same place allows us to both do two things that are unique. First, to tie all the satellites that are in this constellation, this international constellation, that do visit things at the same time of day every day. And the second one is to actually understand the processes that are time varying as a function of time of day. So it's really all hardware, new science.
So one follow-on to that, what about the budget?
So we're doing this mission, what we consider to be on the cheap. It's running about $26 million. By comparison, we took a look at building just another QuickScat-like spacecraft today to be able to do a similar mission, and the budget estimates ran about $400 million.
Fantastic. Okay, if we can get our mic runner over to Sarah Mora. I know she's patiently got her hand up.
Hi, I'm actually really interested in sort of the incubation stage when you're trying to brainstorm how are you going to get data to answer questions that you want to answer, because I would not have thought to do what you're doing with satellites to measure what you're measuring. It's totally fascinating to me, and I just want to know if there's, some interesting aha moments that happen.
You want to talk about the history of scatterometry? Or?
So there's a couple of ways to answer your question. Basically, when scatterometer started up, it was a very dedicated, small thing that 10 scientists in the world understood. Then, as we started to see the importance, especially hurricanes and throughout the world, people sailing and people shipping, the operational agencies like NOAA, the European Center for Medium-Range Weather Forecasting, the Japanese Space Agency, the UK Met Office, all started coming to us and saying, hey, give us your data. We'll put it into our models. And so right now, we get the data directly from the satellites. We process it about really quickly, about an hour, and put it out there so they can use it. And so when you see the weather forecasters, they actually have a wealth of data from different sources, and this is one of them. It also goes into climate models.
All right, next question. Down here in front.
Hi, I'm Anastasia. I was just wondering, I'm a big fan of Elon Musk and SpaceX, but I wonder how everybody works together. Is it an easy collaboration when, it just must be amazing the level of details that you have to talk to the various agencies?
The collaborations are a challenge, where there's lots of government bureaucracy, unfortunately, that's involved. For us to work, for example, with SpaceX, they're actually under contract to the ISS program, which is run out of Johnson Space Center. And so we're supposed to talk to somebody at Johnson who's supposed to talk to somebody at SpaceX. And you have that a lot in government contracting. But fortunately, the people who are involved are all really good people and all really want to do the right thing. And so you wind up building relationships with folks, and you wind up having the discussions you need to have without going through the formal channels, or you catch up later, or you copy those people. Nowadays you just CC 40 other people in your emails, and they're considered informed. But the SpaceX, the SpaceX people are really great. They're new to this game too. They've only had a handful of launches. They've only had a handful of Dragons. And in fact, up until now, there hasn't actually been a science payload delivered through the trunk. The first one is coming up in the SpaceX 3 mission, which is going to have HDEV and OPALS, which are 2 technology experiments. And so we are the first, we're actually the first external science mission really going on the station that's looking down at the Earth.
Yay, science! Woo. Let's see, Bill, I think you had your hand up and you've got a mic.
How much of the operations are handled from the ground, and how much are the astronauts doing on board the space station, if at all, and how do you collaborate with them?
So it's pretty interesting. The astronauts actually hardly even know we're there. They have no role in our operations at all, which is in itself pretty amazing. The main thing they participate in is understanding the safety of adding a payload to the station. Every time you add something to the station, it presents hazards. If we fail in a certain way, we could bring down a power bus. We're emitting microwave radiation. We could accidentally radiate an astronaut who's doing a spacewalk, and so we have to put controls in place to make sure we're not doing that. So they're aware of us from that standpoint, but they have no direct interaction. The operations are actually handled through Marshall in Huntsville, Alabama, and we get basically one of their workstations here at JPL, so we can do all the commanding that we need to do here unless it's safety related, and safety related commands have to be issued actually by Huntsville. The robotic installation is actually done from the ground also, and that's controlled by the folks in Houston.
All right, I think we can take one more question in the house. Right.
Hi, I was wondering, what do you use, what platform do you use to share your data with organizations outside of NASA?
You want to talk about the deck?
Sorry, could you repeat the question?
How do we share data with other agencies?
How we ship data?
How we ship it to other agencies.
What platform do you use to share the data?
So we put it in a computer, and we allow them to have FTP access. So basically, they just come in and suck it into their servers.
NASA has a system of distributed data archives around the country, and we are required to put all of our data into that system. And once authenticated, everybody can get access to that.
So there's 2 ways. I mean, what Howard said is the way we distribute it to anybody. NASA data is free, so anybody can download it. In fact, I come from a third world country. I know that without this freedom of access of data, a lot of the environmental impacts of what's going on in South America would not be at all monitored. So that is a great boon to society in general. The way we do it for the winds, though, is because they need to get it real time. We actually allow them in a special way to come in and get the data from us.
All right, and as we thank Howard and Ernesto for their time, we are going to roll a short video that will give you the RapidScat point of view from the International Space Station. So thank you, Howard and Ernesto. Beautiful, isn't it? I love the lightning, and I love the aurora, and the ocean. So we've talked a little bit about ocean. Jim Graf talked about ocean being very key to our understanding of climate science and climate modeling. And here to explain a little bit more about why the ocean is so important is a JPL oceanographer and climate scientist. His name is Josh Willis. Take note, he is going to show you an amazing trick to wow your friends to explain climate science and specific heat of water. All right, take it away, Josh.
Hey, everybody. How's it going? Yeah, that was unenthusiastic. Come on, how's it going? Yay! All right. Look at this beautiful setup here. I wonder if I can wreck some of it without them getting mad at me. We're going to find out. OK, so my name is Josh Willis. I'm a climate scientist and an oceanographer here at JPL. And I'm also the project scientist for the JASON 3 mission, which is a follow-on mission to the JASONs 1 and 2 and Topex Poseidon, which came before that. And what that mission does is measure the height of the ocean from space. And it's really an incredible technological development, even though it's been around for 20 years. This technology has been doing this particular job for about 20 years. Essentially, they can measure the height of the ocean with an accuracy of about 1 inch from 800 miles in space. So there's a big footprint, and it averages over all the waves and stuff like that. And you can see how tall the ocean is from space. And this is really important to me as an oceanographer because oceans play a huge role in our global climate system, as you can imagine. So how much of the planet is covered by oceans? You guys know? 70 something? Yes, over 2/3. That's right. Over 2/3 of our planet is covered by oceans. And so, as you can imagine, Arthur C. Clarke once famously said we shouldn't call our planet Earth, we should call it planet Ocean, because it's more ocean than it is Earth. So you can imagine that as our climate changes, as we drive our climate into a new realm by adding CO2 to the atmosphere, really almost all the changes are happening in the oceans. So if you think about climate change, if you ask, where is climate change happening? The answer really is in the oceans. We think of it as happening to us because we live in the atmosphere. We think of it happening in the atmosphere, and a lot of times when we talk about global warming, we talk about the rise in the temperatures of the whole planet, the surface of the planet. But in fact, really, it's the rise in temperatures of the oceans. Over 90% of the heat that's trapped by greenhouse gases is warming the oceans. Over 90%. So in other words, the oceans are really our barometer for how much we're changing the climate. And the reason that missions like JASON and JASON 2 and JASON 3 are so important is because they measure that rise in the oceans. If you have an accuracy of about 1 inch over a single spot on the Earth, and then you fly around the planet for about 10 days, you cover almost the entire oceans, then you take this measurement over and over and again, then in 10 days, we can essentially measure globally averaged sea level. Essentially, we can measure the volume of the ocean and how it's changing. So 2/3 of our planet covered by oceans, we can see those oceans slowly rising. And they rise for 2 reasons. They rise because glaciers and ice sheets are melting. Of course, in places like Greenland and Antarctica, and also lots of tiny little mountain glaciers all over the planet. As the atmosphere heats up, as the ocean heats up, these melt, and that meltwater eventually finds its way back into the oceans. So we can see this rising of the oceans from space, from our space satellites. And I like to say that, in fact, this satellite and its predecessors, JASON, this one's JASON 2, I believe, or it might be JASON 3. Anyway, they look almost identical. These satellites are really our yardsticks for measuring global climate change because the sea level rise represents the increase in water. It represents the melting of glaciers and ice sheets, but it also represents thermal expansion. It turns out when water gets warm, it actually heats up, it actually expands. So expanding water is one of the causes of global sea level rise. And we can essentially measure the sum of these 2 things. We can measure the thermal expansion plus the runoff from space using satellites just like this one. And that's really why they're so important. They're really our most accurate tool for measuring global warming. Recently there's been a lot of discussion about a pause in global warming, that the surface temperatures were going up really fast and they seem to kind of level off. And I like to say that paws are for kittens and puppies, and not global warming. Because in fact, global warming hasn't really paused. If you look at any other measure, if you look at sea level rise, if you look at the melting of glaciers and ice sheets, if you look at sea ice loss in the Arctic, all of these things are just continuing on. They're all still happening. There is no pause in global warming. The surface temperature bounces around because of natural fluctuations a little bit, and if you pick the right period, then you can make it look like there's no warming over a period of time. But in fact, better measures of global warming, like the ones that come from these satellites, show that sea level rise is continuing, and in fact, there is no pause in global warming. If anything, global warming is accelerating. So I know there's a bucket up here, and you're probably all wondering why this bucket is here. And the bucket's part of this demonstration that I've been doing for a whole bunch of years now. I like to explain to people why it is that the ocean is really so important for measuring global warming. And like I said before, over 90% of the heat trapped by greenhouse gases is going into the oceans. Now, why is that? Why is all the heat going into the oceans? Yell it out. This is the question and answer part. Because of the heat capacity, yes. Oh, you've seen this demonstration before. Never mind, I'll just... So yeah, exactly. The heat capacity of the oceans is enormous. And water, it turns out water is just really, really good at sucking up heat. And that's why over 90% of that heat is winding up in the oceans. And there's a nice little demonstration you can do. If you take a balloon, you can think of the atmosphere. I like to say that the atmosphere is kind of like a piece of tinfoil wrapped around a hot potato. If you put tinfoil in the oven, you can actually reach into a 400-degree oven and pick up the tinfoil. Why is that? Because the tinfoil has no heat capacity. Essentially, its heat capacity is very small, and as soon as you touch it, it's the same temperature as your fingers. But if you wrap that foil around a hot potato and you pick up the potato, it'll burn you. And the reason is because it's just reflecting the temperature of whatever it's touching. And that's what the atmosphere is like. Really, the atmosphere is just doing what the top 100 meters or so of the ocean is telling it to do. So in a lot of ways, again, as we look to trying to understand how climate change happens, really, all the action is happening in the oceans. So if we take a balloon and we fill it with air, like this, everyone's excited, I can tell. Now, if I hold a flame to this balloon, what do you think is going to happen to the people in the front row? They're going to get splattered, somebody said? I hope not. Our insurance won't cover that. So if I hold a flame to a balloon, it pops, right? You guys ready? I don't think you're ready. Are you ready? Here we go. 1, 2. Yes, I knew I could mess up this set. So the reason the balloon filled with air pops is because it has a very low heat capacity. But if you fill a balloon with water, then it turns out you can stand there with a flame against it like all day, and it won't pop. And I've done this experiment many, many times, and I can assure you that the balloon has almost no chance of popping. Like, it's definitely... How was that for the mic levels? It's definitely almost assuredly not going to pop and ruin this lovely set. But just in case it does, we'll put this little balloon here, or this little bucket here. Now you're all really scared of being on the front row. Okay, so here we go. We're going to hold the flame against the balloon and see what happens. Are you guys ready? Because I'm not. Anybody want to get lunch? Click, click. No one's typing anymore. It's so weird. So I could really stand here literally like all day. I had a friend who's in the audience somewhere. She put a balloon over a Bunsen burner, and it remained intact. Now, if you use a blowtorch, the balloon will pop. Just so you know. But I could stand here for a really, really long time and talk to you for the entire rest of this segment, and the balloon wouldn't pop. In fact, the balloon's not even hot, if anybody wants to touch it. Yeah.
Water or ice water? Wow.
It's not even hot. So go home and try it someplace safe with your own garbage bag. And let's see if I can... Science!
Josh, we've got some time for questions. Do you have some time for questions?
I have some time for questions. Do you have questions?
Who's got questions?
Who's got a question?
Well, there we go. Wait for a mic runner to come to you, and your question will be answered.
Hi, I have 2 questions, so if that's not fair, just answer whichever one. The first question...
We'll see what they are.
The first question is, as a scientist who works in tracking global climate change, is there any scientific basis for skepticism about climate change? That's my first question. And then my second question is, how far away are we from runaway greenhouse effect?
Oh, okay, 2 great questions. So with regard to the skepticism question, I guess I would say that climate science is all about skepticism. In fact, as a scientist, I'm probably the most skeptical person in the room. But with regards to what's been proven in terms of climate science, we've proven really beyond any doubt that humans are the biggest factor driving climate change today. So we've had a very stable climate for about 10,000 years. And then in the last 150 years, we've started to completely change the atmosphere. We can measure that. We can actually take the carbon out of the atmosphere and weigh it, look at the isotopic ratios, and see that that carbon came from burning fossil fuels. And we also know from the basic physics of how carbon dioxide interacts with light as it comes in from the sun and outgoing radiation as it goes out from the Earth, we know that that carbon dioxide is going to trap extra heat. And we also know from the climate records that things like sea level rise were stable for thousands of years. We had 2,000 years with almost no sea level rise. And then in the last 150, boom. So we have a really good chain of evidence holding together our knowledge of human-caused global warming. So if your question is about, is there doubt that people are causing global warming, really there's no doubt anymore. Skepticism, of course, in science is an incredibly important part of science because if I try and publish a result, immediately what happens is, if I say X is true, then I write it down, I send it to all my peers who don't really like me that much anyway. They tell me all the things that are wrong with it, they send it back to me, I try and fix it, they read it again, they send it back to me, and after it goes through this iteration process several times, finally, I published a paper that a whole bunch of my colleagues can agree on is true. But that's not the end of the process. Eventually, somebody else will publish another paper and another paper and another paper looking at the same results over and over and over again. And it's through that process that we built this tower of knowledge, which is really hard to knock down with a simple, I don't really think that's true. So in terms of is there skepticism, well, skepticism's a part of science. But is there doubt about human-caused climate change? I think the answer is no. Runaway greenhouse gas effects, we're still finding things in the climate that might trigger stuff like that. So we don't have a good idea of when that might really happen. Sometimes warming up the climate adds more CO2, which warms the climate even more because of carbon dioxide trapped in these different places. So I think that the answer to that question is sort of, we don't really know if we're close to a runaway greenhouse effect.
All right, next question. Oh, we have a mic on the other side of the room. Thank you.
With regard to the ocean height change, what kind of percentage is coming from the density change of the water as opposed to the ice caps melting and runoff and things of that nature?
Oh, that's a great question. It's about 1/3 of sea level rise today is caused by warming and thermal expansion. The other 2/3 is the melting and runoff. But looking out into the future, it's going to tilt way more towards melting and runoff because there's only the oceans can only absorb the heat so quickly, but you can melt an ice sheet really fast. And so in the future, we expect it to be more and more melting and less thermal expansion or density changes.
All right, let's see, where'd our microphone go? Yeah, Ray, you had a question? Ray Beta? Okay. All right, I love it. So many questions.
Everyone's so polite. My question is actually less about the science than the outreach. When you're doing fact-based work, but in a field that's been artificially politicized, how do you use and what tools do you turn to reground the conversation in facts?
Well, so that's a fantastic question. The tool that I like to use, as you might have already guessed, is comedy. I think making things funny makes them more accessible and less a threat, less a challenge to people's worldview. But I think you have to be cognizant. We have to be thoughtful when we communicate about climate science, especially in this. However we got here, it's a politicized topic now. And so we have to be a little bit thoughtful about how we communicate. And I think that, as scientists, we often communicate, we think a lot about uncertainty. So if you ask a scientist a question, 99% of the time they'll tell you what they don't know instead of what they do know. And I think the simplest thing we can do to make lives make our lives easier is talk more about what we do know. But personally, in my own personal voyage through science and science communication, I really like making people laugh because I think it's super fun, and also because I think people, it's easier to learn, I think, and absorb information, especially complicated information, if you're having a little bit of fun. And I like to have a little bit of fun. I had a college professor in math. He used to say, "It's fun to have fun."
Profound, profound. All right. You there with the microphone. What's your question?
Yeah, so I think a lot of us are aware of what's going on the land, and it's really interesting that you're studying the ocean. Some of the other presentations talked about how satellites were able to see things that, say, airplanes or boats weren't able to see, or buoys. So I was wondering if maybe there were certain things that you've learned through the years from looking down from space on the oceans that just were interesting to you.
Oh, absolutely. That's a fantastic question, and I think it's one of the reasons why NASA is such a special place to do this kind of work, because climate science, climate change is happening to the whole planet. But we can't fly an airplane high enough or put enough buoys out to kind of see the whole planet all at once. And satellites allow us to do that. There's some trade-offs that you have. Like, for example, our altimeter satellites, our sea level satellites, can't see below the surface. They can't tell us what the temperatures are doing, and mostly a little bit they can tell us about the currents, but you can't see below the surface of the ocean from space very well. So you give up something, but what you get is this big picture. And things like El Nino have really been revolutionized. So we knew that El Ninos happen in the Pacific Ocean, and just to remind you what an El Nino is, there's a big pool of warm water in the western Pacific, and every couple of years it slides over to the east, and it wreaks havoc on weather patterns all around the world. And we knew that it happened, and we kind of knew the physics of it from other things, but satellites showed us how global that effect can be. So we've seen impacts of El Nino as far away as Antarctica and Greenland. So it really gives, and you wouldn't have even thought to look for that if it wasn't for something giving you this kind of big picture. You can see it all at once. The other thing it gives us is global sea level rise, which in my book, like I said, the yardstick of global warming. So those kinds of things you really couldn't do without satellites.
All right. Let's see, who's got the mic? Who's got the mic? All right. It's a game of hunt the mic. There we go. No, Jari is right behind you. And Bill is right in front of you.
Oh, that was a race.
Next one's yours. Actually, let's go ahead and get the mic into the hand of the next person. Any other questions out there in the house for Josh? Right here. So, Jari, if you want to bring the mic on this side.
Right here,
oh, right there. Aha.
But when and where is Jason launching?
It's launching in 2015 out of Vandenberg. Hopefully, unless our budget gets slipped again.
I was just wondering, I know that most astronauts have a combination of diving, a love for the ocean, a love for the air as pilots. I wonder if when you become an oceanographer, if you're a diver yourself, and you use that for some of your...
I'm the lamest oceanographer in the history of oceanography.
Never.
I haven't dived. I don't dive. And what's even sadder is I spent 8 years in San Diego, and I never learned how to surf. So, anybody want to teach me how to surf? I'll be happy. Yes. All right. But I do have other hobbies like comedy.
That's right. You do improv, don't you?
I do improv. Yes, I have I'm taking classes at the Second City in Hollywood and trying to do
comedy and science not mutually exclusive. They're two great tastes that taste great together. Right. Okay, now.
So this is going to go back to boring science question, I guess. So you've shown how great the water is absorbing heat. How long does it take to absorb it compared to releasing it?
Oh, absorbing it? Well, that's a really tough question. How long does it take for the ocean to spit that heat back up, right, that it's absorbing? Yes. It kind of depends where it lands. There's places in the North Atlantic where water leaves the surface of the ocean and it dives down and it spreads out underneath the rest of the ocean, and it takes like 2,000 years to get back to the surface. So there is that time scale in the ocean. On the other hand, If you heat up the tropics in an El Nino, then that's going to stay warm for a year until some other climate phenomenon changes it. So it's anywhere, depending on where the heat goes in, anywhere from 1 year to 2,000 years, I would say. Somewhere in there in the middle.
Are there going to be any efforts in the near future to measure heat changes in the deep ocean?
Yes, actually. Heat changes in the deep ocean are really important and are part of this same question. How much heat is really getting down there, and it's going to be down there for 1,000 or 2,000 years? We don't really know because we don't have good measurements of the deep ocean. And there's a program called Argo, which are little floats that go up and down in the ocean, little robotic floats that are autonomous. They drift around. And they're right now they essentially measure the top half of the ocean, the top 2 kilometers. On average, the ocean's about 4,000 meters, 4 kilometers deep. And getting that bottom half is kind of a technological challenge, but there are efforts underway at NOAA and other places to try and develop, and Scripps Institution of Oceanography, to try and develop floats that'll go down that deep and come back and have good data and all that stuff. So there are efforts. And we have some tools, like you can drive a ship around and lower an instrument over the side, which we've been doing for 135 years now. We know how to do that pretty well, but the problem with that is getting enough of those data to really see the big picture. And there's lots of work to develop that. You can kind of figure out a little bit of it by sort of subtracting a bunch of really big signals to get a really small number. So we can measure the total sea level with our JSON satellites. We can measure what's going on in the top half with Argo. And then the other thing you need to know is how much extra water there is. And there's another satellite called GRACE, which measures, essentially weighs the ocean. So using all 3 of those, you can kind of infer what's going on in the deep ocean if the signal's really big. But right now, we don't have a long enough time span of all those data sets to see what the signals are down there. So maybe someday we could do that with a combination of other data sets. But the right way to do it is to stick little floats down there, and people are working on that.
Okay, this is the dumbest question on Earth, so yes. I apologize in advance.
Wow, I didn't know we were going to set records today. This is awesome.
Right.
I'll do my best.
Bring it on.
I've heard a lot about the danger of the oceans rising and all of that, but I'm just wondering how far out has that been projected? Hypothetically, if everybody moved away from the coasts and the ice caps melted, would it cover land?
How far do I have to go inland before my property value goes back up, right?
Or where is the next beachfront property?
Right, where's the next beachfront property?
Futures and...
So the numbers are kind of like this. Sometime in the next 100 years, we'll probably get between 2 feet and 5 or 6 feet of global sea level rise. So it depends a lot on what coast you live on. And doing a better job of between 2 feet and 5 or 6 feet, we can't really do that yet. We just don't have the scientific understanding of things like these ice sheets. So Greenland is covered, and Antarctica are covered by these giant just blobs of ice. They're so big and so heavy, they push the land down. And in some places, they actually are below sea level, so there's water up against the side of them, kind of eating away at them. And how all those things interact, the atmosphere dumping snow on the top, the ice sitting on the land, which can come up when the ice disappears, the water coming in from the side. You can see it's a really complicated thing. And so understanding what the ice sheets are going to do, that's our big uncertainty for future sea level rise. And right now, that's what's limiting us from saying anything better than somewhere between 2 feet and 5 feet. Now, what that means practically on the beach depends a lot on where you live. In places like New Orleans, where it's sinking, another foot of sea level rise is a really big deal. In South Florida, it's also a really big deal because the land doesn't rise very high as you go in from the water there. There's a lot of places that are vulnerable to even 1 foot of sea level rise, and we're almost certain to see 1 foot in the next 100 years, probably in the next 50 years. So those are kind of long time scales for like a home mortgage, right? But they're not long time scales for 2 home mortgages, right? So your home, you may have to worry about, but your kid's home and your grandkid's home, they're definitely going to have to worry about sea level rise. So it's out there. The thing about sea level rise, though, is that it doesn't, global sea level rise happens in this steady, long-term way. We're talking about numbers 50 years from now, 100 years from now. But practically speaking, when you live on the beach, it's not that gets you. What happens is you have a little bit of extra sea level rise, and then some storm that wouldn't have hit you before hits you now. And the instances of things like that are starting to happen, like Sandy, like Katrina. Those didn't happen because of global warming, but they were worse because of a bit of extra sea level rise. We've already had about a foot that's essentially man-made. And we'll get another foot. And so those things are going to happen more and more frequently. So it kind of happens all at once. And property values, that's a tough question because that depends on how risky people think it is to live somewhere. And so when they start to think that it's risky to live in this flood zone, then the property value goes down, everybody moves away. So it's a weird thing. So I didn't really answer your question. But I talked a long time.
Okay. I think we've got, right. Oh, you've got it. You've got it. And now the floor is yours. All right, bring it on.
So another probably silly question is, with that knowledge that you just shared, is this global or this sea level rise, is it an inevitable freight train that our kids just have to know where to go buy property, or is there something that they can really do to make the difference between that 2 feet and that 5 feet?
Probably is the answer to that. Certainly, if we curb emissions, if we don't put as much CO2 in the atmosphere, we'll have less sea level rise in the long run. And it'll probably happen slower. But just how much is still really hard to say. But that doesn't mean we shouldn't do anything about it. Definitely, we should be trying to curb our emissions. We should be looking for alternative sources of energy. And personally, I think, even though JPL may not want me to say this, I think that, that we should have something like a carbon tax, because we don't really pay the cost of the carbon that we put in the atmosphere. People down the road are going to pay that cost. So we should be paying that cost now to help ourselves avoid the worst potential problems that we see down the road. So yeah, there's a lot of stuff we can do. We can still stave off the largest scenarios, the fastest warming, the most sea level rise, but we got to do something pretty soon.
All right, our last question is right down here in front.
Hi there, my name is Govindani, and I had a question about, Jason and all these other 17 or so satellites that NASA has mapping every aspect of the surface of the Earth. Are there any places of mystery left on the planet that have not been thoroughly mapped? And that's one side of my question of asking, are there any places where you really don't have as good a view on the Earth, or things that are still somewhat mysterious, say in Antarctica or the Arctic, that you'd love to get a better look at?
Yeah, that's a great question. The answer is yes. I don't have a comprehensive list of all the places that we can't see, but let me tell you about one that I think is really interesting and will be an important forefront in our future, and it's because of this sea level rise question. So the places where the ocean meets the ice, the places where oceans are beginning to intrude on these ice sheets and eat away at the bottom of glaciers that run into the water. Getting up close to those places and understanding what's going on in there is really the key to answering this difference between 2 feet and 5 feet of sea level rise. So, of course, there's frontiers. You know, there's places in the bottom of the ocean we haven't been. It's hard to see the oceanography in places like the Arctic, where it's covered by sea ice most of the time. But to me, I think the biggest frontier really is looking at this kind of junction between water and ice and land and air, really, all of them kind of coming together to be important in this one sea level rise problem. That's really where I think the new frontier is, and where we're going to have to push for new technologies and new ways to delve into these regions to really figure out what's going on and really answer this big question of 2 feet or 5 feet.
All right, thank you so much, Josh, for answering all of our questions and showing us a great party trick.
Thank you, guys.
Now, for something completely different. How many of you waved at Saturn? Remember the Wave at Saturn campaign, right? That the Cassini spacecraft was out at Saturn, and it swung around to take a picture of the whole Saturn system, but guess what? Earth photobomb the shot. So let's go ahead and take a look at the picture that Cassini returned to us. That's here, that's home. Yay, Cassini! And I'm sure that you could pick yourself out waving in that shot. All right, so we've talked a lot about water and the water cycle. What about the carbon cycle? Carbon dioxide gas is something that we're very interested in studying, and also looking at the way that carbon moves around our planet. So we do want to run a short video for you to tell you a little bit more about the carbon cycle and about an upcoming mission, the Orbiting Carbon Observatory 2, or OCO2. So let's go ahead and take a look at that video.
When it comes to carbon dioxide in the atmosphere, we've all heard a lot about where it comes from, but what happens to it once it gets there? Lots of things, actually. The atmosphere, oceans, forests, and soil are all constantly trading carbon dioxide with each other in a global exchange called the carbon cycle. Some parts of this cycle are sources of carbon, while others are sinks. All of these natural sources and sinks are pretty well balanced. Just as much CO2 comes out of the atmosphere as goes in. But now we've got a problem. Ever since the Industrial Revolution, we've been tipping the balance, adding a CO2 source without providing a sink to match. Some of this extra CO2 is being taken up by natural carbon sinks, but not all of it, and on top of that, the efficiency and availability of these sinks may change over time as they react to changing climate conditions and as we clear forests for agriculture or homes. If we want to know what's really going on with the carbon cycle and how it may affect climate, we need more information. After all, we can only manage what we can measure. That's where the OCO2 mission, the Orbiting Carbon Observatory, comes in, NASA's first satellite designed specifically to measure the global distribution of atmospheric CO2 from space. How will it do that? By measuring the sunlight that bounces off the Earth's surface. On its way through the atmosphere, this sunlight interacts with CO2 molecules in the air. CO2, like other gases, absorbs only certain colors of light. OCO2 is tuned to look at these specific colors, and by measuring the amount of light that's missing in each one, we can figure out how many CO2 molecules got in the way. As OCO2 orbits the Earth each day, it will make hundreds of thousands of CO2 measurements. This high measurement density will give us far more information about where and how CO2 is traded between sources and sinks. Plus, measurements collected over weeks and months will capture the variations due to seasonal changes, allowing us to watch the planet breathe. If we can understand better where these carbon sinks are and how they store carbon dioxide, we'll know a lot more about the processes that control the rise of CO2 in the atmosphere and what role it might play in our changing climate. So take a deep breath and get ready for OCO2.
Orbiting Carbon Observatory 2, or OCO2, is NASA's first dedicated Earth remote sensing satellite to study atmospheric carbon dioxide from space. We're going to meet two key people behind the science of this mission. First up is Annmarie Eldring. She is the deputy project scientist for OCO2, and she came to California 25 years ago to study local air pollution, something close to my heart and lungs as a local. And now she's getting ready to take global measurements of carbon dioxide and greenhouse gases from space. She is joined by Mike Gunson, the project scientist for OCO2. He manages the Global Change and Energy Program here at JPL, and he's been a leader for 3 different satellite and space shuttle-based atmosphere experiments at JPL to measure Earth's atmosphere. So I will step aside and let them tell you more about what they do on a day-to-day basis and the science they're excited to do with OCO2.
All right, thank you very much. Hi, everyone.
Morning.
And thanks for having us here to talk about OCO2.
Yep. Anybody spell football S-O-C-C-E-R out there? Any Manchester United supporters out there? Oh, I'm going.
Michael, relax. I'm sure we can get them excited about the soccer at some point. So
That's
this is what I get
work.
to deal with on my day-to-day basis. I'm doing science, and I'm finding out about the soccer score before I come to the office. It's rather important. So Mike and I are the project scientists and the deputy project scientist, and our goal is to make sure that when this satellite, this is only a 1/10 scale, it's actually a little bit bigger, but when our satellite gets up into space, that is going to be able to do the science that we want to do. So making sure the instrument's built to the specifications and that our team members are ready to take that data when it arrives, do the analysis so we can provide the CO2 measurements, and then helping interface with the science community that's going to do a lot of the work afterwards. So that's kind of a short description of a project scientist.
Very short description. Herding cats comes into it somewhere, I'm sure. Actually, we'd just like to give a call out to Dave Crisp at the back of the room. He's the science team leader, Dr. David Crisp. Most of our time is inevitably spent in, I'm often asked, what's it like to be a scientist? And I don't know that a project scientist is that much different than, say, the work that Josh does, except he's far funnier about it. And most of my colleagues, 95% of it is pretty much heavy lifting of grunt work. And then you get, every now and again, there's about 5% where you learn something. And I do have fun every day. Do you have fun every day?
I have fun every day, but I'm very excited because in July 2014, we're actually going to launch this thing into space and get real data. So we've been working for quite some time, and Dave has been working for even longer to see the OCO2 instrument built and launched. And actually, you may wonder, why is it OCO-2? If you're a chemist, you'll realize that's a little bit of a confusing nomenclature. Well, really, this is the second time this has been built, because they built an OCO instrument and launched it into space, but the rocket did not work properly, so the thing went back down in the ocean in 2009.
It's swimming with the fishes.
It is. And NASA decided this is such an important data set that they would go ahead and rebuild it, so we are the rebuild, or OCO-2, of this, a carbon copy of this satellite.
Unintended.
It burns, it burns. Josh has opened the gates for comedy and science. It's a little bit of a Pandora's box.
We've even had a Monty Python reference. Well, how good can it get? And now for something entirely different.
Now for something completely different in the show at some point. If I didn't, I thought about it. So, so the video that you rolled that we had at the top of this segment is really jam-packed with information. So maybe you could talk a little bit more of exactly how OCO2 looks at carbon dioxide in the atmosphere.
Dr. Gunson, would you like to explain that?
You passing me that one? This is the hospital pass. Okay. So as we've devised a technique that looks at sunlight reflected off the Earth's surface. So that light has come in, passed all the way through the atmosphere, bounced off the surface, and comes back to the satellite and the instrument. By looking very carefully at different colors of that light, at different wavelengths, we can actually find the light which is affected by the amount of carbon dioxide in the atmosphere. Now, the trick for any experiment like this that involves carbon dioxide is that we have to be able to do this very sensitively. I think most of you might know that the background amount of carbon dioxide in the atmosphere passed 400 parts per million. It was in the news probably in the, was it March, April timeframe. What we're looking for are changes in that amount by 1 part in 400. 1 part in 400. So that's a very tiny variations we have to be sensitive to. So we measure that sunlight really well. We spend a lot of time as a science team characterizing the instrument so we know how it performs in exquisite detail is probably the best way to describe it. That way we can discern how carbon dioxide is changing so you can know whether it's being put in the atmosphere or it's being taken out by something at the surface. Most of the carbon dioxide in the atmosphere, he said, going on past an explanation of how this works. Once carbon dioxide gets in the atmosphere, it's really inert. Nothing affects it while it's in the atmosphere. The only way you lose it out of the atmosphere is if that molecule of carbon dioxide collides with the surface. A plant or the ocean. That will take it back out of the atmosphere. So we're looking for very small changes in something that's going to be with us for a very long time. So I was impressed with Josh's answer, by the way, about what does the future for hold. We're putting stuff into the atmosphere at a rate of knots, we as human beings. And we've already bought into the changes that will cause, and we won't see, even if we stop tomorrow, we won't see the effects slow down for another decade or two, because there's a kind of a buy-in factor. Once you put it up there, it has a long-lasting effect because it hangs around a very long time.
So we do have the Keeling curve animation, if that would be helpful to you in your discussion of CO2. Would you guys like to take a look at it? Sure. All right. Let's see if the booth can go ahead and pull that animation up for us.
So the Keeling curve, you may ask the question of why the Keeling curve, and that's because Professor Keeling down at Scripps Institute started these carbon dioxide measurements actually back in the 50s in Hawaii. And this is an animation that's showing you how it changes over a few years. And you see this up and down with the seasons, and that's basically, as Mike had said, that the plants are actually a big drawdown of CO2. So as they grow in the spring, the CO2 goes down, and now you see the fall. As they start decaying, they release that CO2 back up into the atmosphere. So especially in the northern hemisphere where we have a lot of forest and trees, you see this annual up and down. But on top of that, the whole curve is growing over time, and that's because of this unbalance that was mentioned in the video, that as humans put these emissions in, the natural source, the natural methods to take it out of the atmosphere can't keep up with all that we put in. So bit by bit, we're increasing concentration. And this is just showing, I think, over a 10-year period or so that it increases from 370 to 380. And as Mike mentioned, we hit 400 this year already.
So the interesting part about that curve, and it's something that I find, I probably put my arms around about how profound it is that it's going up steadily, but half of what we've ever burnt in terms of oil or coal is still in the atmosphere. And somehow, and the big science mystery, is somehow the Earth has managed to continue to take 50% of what we put in out on a continuing basis. That's kind of the good news. It hasn't, so we can keep putting more and more and more in, and every year we burn, actually we do burn more fossil fuels every year. We burn more coal, we burn more oil. But half is still being drawn out. That's kind of a remarkable thing, just a remarkable fact. And what we'd like to find out is why is that, and what's going on that would either stop that being true in the future or change it today. Because if any of those things slow down and we continue burning a lot more fossil fuel at the rate we are, we could see a sudden acceleration in the amount of CO2 buildup. The airborne fraction is a phrase I've heard recently. The airborne fraction could continue to increase. And that would be not very nice.
Well then, with that...
Oh yeah.
All right, we're supposed to be positive.
Yeah, we've got to be positive now.
Let's go ahead and turn things over to the house here. Who's got some questions about carbon emissions and OCO2? Okay, here comes Bill with the mic.
I have one quick question and one kind of more general question. The first is, between the first OCO and the OCO2, since you had the time, were there any adjustments you made to what you were either going to collect or how it was going to work? And the second is, we've heard about carbon emissions, wind over the water levels. How do you, what's the process that determines what data your limited resources are going to be focused on collecting, if that makes sense?
Money.
Yes. Okay, so the first question was the...
Changes in the...
change in the instrument. So carbon copy is our mantra because the cost of doing something is going to go up if we make changes. So the whole mentality was keep it the same unless, for example, some of the things just couldn't be bought anymore. So there's a few small changes where things could not be obtained, but generally we didn't do anything just to make it better.
This is, it's kind of unusual for NASA. We always you were listening to Josh and how the JSON series came about. Each one of those was a little bit better than the preceding one. But there's a price you pay. I mean, there's a development cost in real dollars. So the plan here to realize this as quickly as possible, we chose to do everything almost to the letter the same.
And in terms of the data that we want to collect, there's kind of a balancing act because the clouds that are around Earth make our measurement difficult, right? So Mike talked about the reflected sunlight. So when it's cloudy, we don't really get to use that data. So the first thing is we're going to measure all around the Earth hundreds of thousands of times a day, but then the clouds will probably make 80% of that data impossible to use. So we have maybe 20% we can use, but then it costs a lot to run all the computers to analyze it. So our goal right now is based on what the scientists need to answer these questions, we'll process as much of the data up to maybe 6–7% of it. And then we're trying to find ways to process more, like work with the supercomputers or other places where we maybe get the capacity to process all the data.
Cloud computing, whatever resources we can find.
But there's sort of basically driven by what the scientists need to answer the question, we've tried to size the data that we're going to get.
So at the bottom of the day, it was $1. It was $1 issue.
$1 issue, yeah.
All right, next question.
So on each upswing of that Keeling curve, I sort of noticed a little bit of a saddle point before it peaked during each seasonal rotation. Could you guys explain a little bit about what that might be caused by?
That's a really good question. I've never looked at that in detail, actually. I know what the drawdown is due to. I don't know whether that's because oh, Dave does. I'll put $5. I've got $5 in my pocket that says Dave knows the answer. Intertropical convergence zone movement.
To some extent, actually, that little bump in wiggle has to do a lot with the fact that you're making pretty much a single measurement of the atmosphere in that curve that's shown there. And it actually represents changes in the atmosphere that are due to changes in plants over the whole Earth. Now, as you probably all know, there's a lot more land in the north. And so what we're mostly sensitive to is it's fall in the north, and the trees are all losing their leaves. But guess what? It's spring in the southern hemisphere. It's smaller. It makes a smaller impact on the total system. But a lot of that little wiggle you're seeing is the peak growing season in the south coming in and influencing that carbon dioxide just a little bit. But you can kind of see how much of an impact we have in the northern hemisphere with its much larger continental area compared to the southern hemisphere. And that also tells you that most of those bumps and wiggles have to do with the carbon cycle with trees and plants on land. The ocean is kind of steady all year long. So since you have more ocean in the south, you don't see a big impact there. But you do see an impact, and it's that little bump.
If you look at the same kinds of measurements made on the North Slope of Alaska, the depth of those troughs is much deeper because they're influenced by all the trees and the forests in the northern hemisphere and less influenced by, it takes a while for the influence of what goes on further away to reach the North Slope. But the depth and the cycle is much bigger if you looked in other places like the North Slope of Alaska, for example.
All right. Next question.
So this is more of a general question. I mean, I'm sure NASA has a lot of great ideas for missions in general for Earth science. How do you guys decide which missions fly, or who decides that even?
So the one strength about NASA, and I personally believe this is a significant strength, is its strong relationship to the research community. So NASA, unlike other bodies like the Department of Energy or the Department of Interior, its primary customer base is the research community, scientists. So the way that these things are usually selected is by the community coming together and saying this is an area of interest, or by, in this case, Dave was the leader of a proposal to NASA which outlined the science value of the mission, outlined how to do it, and that was reviewed by the science community and said that's something we ought to do. So the decision making is really a collective one in the science community by evaluating how good the idea is, whether the science questions are important, and whether it can be done. And then that usually is the information that guides NASA in deciding what steps to take.
And I think another important thing is to remember is that competition is actually important. So it's community driven, but a lot of us spend a lot of time, we write proposals for these types of missions, and then they get evaluated by a big panel. And so the one that's the most convincing and shows that it has good questions and they can be answered and they can do it in the time and budget. So it's a way to get the sort of the best bang for the buck, because everybody's fighting to do a really important thing with the least amount of money.
Okay, we have time for exactly one last question, and it needs to be quick, and this is a challenge to our scientists. Ready? Go.
So where I'm from, originally Southern Ontario, we are into solar energy and using solar power. My brother has solar panels on her. And there are a lot of turbines, wind turbines. I wonder how long it's going to take. As Josh was saying, it takes like 10 years. Will you see a measurable notice or difference in your measurements in the future?
So it's a really interesting question. If you look at, and this is not what we can really pin down from this experiment, but if you look at the economic data on where fossil fuels are being used, there's two things. Developed countries, and Europe in particular, but in the United States as well, our per capita use has been steady for decades. In places like Sweden, for example, it's declined. They've transitioned to a large amount of hydroelectric power. Second, the current increase is in the developing world. So now, somebody asked me this question the other night at a Pasadena forum on climate change, and I had to disagree with him afterwards and saying it's less about us now, it's really, really about China and India. Their per capita use, to give a measure, is a tiny, tiny fraction of our per capita use. So their potential to achieve, modernize their societies is huge. Will we see a difference in sustainable energy alternatives? The trick is you have to use, if you don't have anything else, you have to burn coal to make something to replace it. You have to burn oil to replace it. It takes a long, long time to get that payback, and you can see it if you ever install solar power, that the payoff time isn't 2 to 3 years, it's like 10, 15, 20 years. So in order to get there, you have to start small, but the payoff time in replacing and trying to migrate away from fossil fuel-based energy is a long, drawn-out business.
Thank you so much. Please, a big round of applause for our experts from OCO2. All right, so that concludes our speaker program for this morning. But for those of you here in the room this afternoon, you're going to go down over to our clean room where you're going to be able to see these spacecraft being built, RapidScat and SMAP. You'll be able to look down in the clean room, seeing them build them. And some of the engineers from the mission will be up there in the gallery with you to answer some of your questions. And OCO2 is currently being built in Arizona by our contractor Orbital. So 2 out of the 3 are here. Now, as I mentioned at the start, these missions are launching in 2014. We will be holding NASA socials for each one of those launches. So especially for people watching today, if you like what you see and you want to come behind the scenes and learn more about our missions, please do follow us at NASA, at NASA JPL, or NASA Social, and you will learn when these events are coming up. RapidScat will be launching from the East Coast, from Kennedy Space Center, and let's see, SMAP and OCO2 will be launching from the Vandenberg Air Force Base here in California. We're going to show you one more picture of Earth from space. Now, Cassini, that was taken from, I believe, 900 million miles away. On Valentine's Day in 1990, Voyager, and that's Voyager right there, looked back to take one last picture back at Earth that we all know as the pale blue dot, and we'll show you that one right now. All of us on that